still got another minute or so in case we get distracted. Alrighty, we'll go ahead and get started. So this one's a soil health perspective in diverse western U.S. ecosystems by Jim Ippolito. Is that right? Did I? Okay. Wow, that was a good guess, I guess. Alright, so I'll just quickly read his bio just to introduce him. So Jim Ippolito received his bachelor's in plant science with a concentration of agronomy. Oh my goodness, agronomy. From the University of Delaware in 1989 and a master's in 1992 and his PhD in 2001 in environmental soil chemistry quality from Colorado State University. He worked for CSU from 1989 to 2007, focusing on beneficial reuse of organic-based materials in production agriculture settings. He then worked for the USDA ARS in Kimberly, Idaho from 2007 to 2016 as research soil science focusing on water and soil contamination issues and soil health. Jim currently works for CSU as a professor in soil fertility and soil health in the Department of Soil and Crop Science. His research focus attention on qualifying soil health in dryland, irrigated agroecosystem, grazed rangelands, pasture grazed land settings, organic agroecosystem, CRP, and mine reclamation sites in the central and western U.S. So go ahead and welcome Jim up.
Good morning. Thanks for that introduction. Again, my name's Jim Ippolito. I work at Colorado State University, and I have to apologize in advance. I mean, following Jill's talk is impossible. There is no way. I've only had this happen to me a few times in my career where I followed somebody who just, wowed me, right? I mean, that was really good. So I'm sorry that this isn't going to be that good. There's no way this is going to be that good. So I've been working in the soil health arena for almost my entire career, since 1991, when we used to call it environmental soil quality, where we focused on soil physical, chemical, and biological attributes and how they came together to improve ecosystems or agroecosystems. And, from that introduction, I'm all over the place. I work in dryland and irrigated ag. I work in forest fire burned areas, grazing lands, pasture lands, mine lands, areas that are contaminated due to mankind, like lead smelter industries in China, and how that affects humans and plants and animals. And maybe you can tell from that bottom right-hand picture, that big smile on my face, I just really love what I do. And it just so happens that picture is at the base of the tallest peak in Colorado, Mount Elbert. So, I mean, talk about a great place to go and work, and you're out there and you're sweating in the middle of the summertime, and you look up at 14,000 foot peak, and you're ear to ear with that big grin. And I just really love what I do. I'm assuming that will come across in this talk. Am I good to go? There it goes. Okay. So I'm going to tell you a bunch of stories. And it's all my stories are focused around soil health. And I'm going to tell you some stories from research so that this talk really sort of bridges the gap between some of the presentations you've seen over the last day or so in terms of, more, I would call it real world versus my world, which is the playland as a scientist. I'm a soil scientist. And so I want to try to bridge the gap with some science behind what you've probably seen and heard over the last day. So what is soil health? You probably all have a pretty good feeling for what soil health is, and I've gotten used to presenting soil health in this manner. And I focus on, it's not going. Yeah, this needs to begin. Yeah. Okay.
It doesn't like this YouTube connection.
Mhm. All right. Perfect. Okay. So what is soil health? And like I said, this is how I really like to present soil health. And I do this for a reason, because when I started talking about soil health, which was environmental quality for my entire career, I started talking about soil health to producers in eastern Colorado about 5 or 6 years ago. And I saw a lot of eyes rolling. And so I switched gears in terms of how I present the concept of soil health, and I do it in the context of human health. And I probably could have shown pictures of me when I was 15 and when I was 25 and how I feel like I look now, but I'm going to show you the cartoons. And you might ask, okay, you look at these three pictures of these three cartoon individuals, and which person is the healthiest? And so when we quantify human health, do we ever quantify directly human health? No, we don't. And so the way I like to present soil health is with regards to human health. And if we were to take these three people and ask them to run a marathon, and before they do that, they better go to their doctor and see if they're fit enough to run a marathon. And so if we were to do that and send them to a doctor, what sort of physical, chemical, or biological characteristics would a doctor look at? So in terms of physical, they would probably put these three individuals on a treadmill and hook them up with a mask, right? And measure VO2 max. How much oxygen can they take in? It's a quantity of probably physical health, one attribute. In terms of chemical, all of us in this room have probably had a chemical health test done, whether you know it or not, right? By having a blood draw and looking at constituents like cholesterol content, for example. Now, is that a measure of health directly? Probably not, right? But it tells you something about how healthy or not you are, possibly. And then in terms of biological human health, we don't have this test really per se, but my microbiological friends tell me that this is probably coming, where you're going to have a stool sample taken and they're going to look at your gut microbiome to see how healthy or not your gut microbiome really is. And so when we quantify human health, we never directly quantify human health, do we? And so this is where the eye rolling came in and the aha moment for me came in, because we do the same thing with soils, right? We never quantify soil health directly. We quantify attributes that we relate to health of the soil. And you've probably heard this time and time again over the last day or other places. And so when I think about soil health, I love this picture. And I'm going to ask you, which soil is healthier, the one on the left or the one on the right? Why? It's dark. Yep, organic material. Palatable. Yeah, if I was going to eat the soil on the left, my teeth would fall out. Malleable. Yeah, all right, not palatable, but it could be palatable. It has good tilth. I can't. Yep. I know. It would probably be delicious. And it's probably delicious, following up with what Jill was talking about just before we walked in here. That is probably full of life. And you would be correct. And the kicker with this picture is that they're the same soil, just treated poorly or treated well. The soil on the left was treated via 10 years of conventional or moldboard plow tillage. The soil on the right, I think it says strip till or something like that, but it's basically minimum till practices. And then if you look at the picture on the right, you can actually see residue in the background, right? So you have soil armor in place. You're protecting the soil and making it, quote, healthier based on some of the principles or practices or indicators that you just mentioned. It's darker, it has more organic matter. It probably has more life because you're feeding carbon to the microorganisms that are causing nutrient cycling and turnover. It has good tilth. It has good physical structure. The soil on the left is, as a soil scientist, we would consider that massive. That's a brick. If you were a plant, and Jill showed a great picture of a soil that was compact. It was a drawing, right? Remember, compacted versus good tilth, and the roots were struggling to move their way down. They would struggle in the soil on the left, certainly not the soil on the right. And this is the premise behind soil health. These factors that all of you just mentioned in this room. And so how do we quantify this? I think, and I probably should have reversed those cartoons, because maybe, I don't know why I think this, but when I look at those two cartoons, the immediate thing that I think of is this: the person on the right, the cartoon on the right is probably not as healthy as the person on the left. And I could be right or wrong. But we quantify those factors in soils much like we do in humans. And when we do this in soils, we quantify physical, chemical, and biological attributes. And in soils, you already know this from some of the talks you've seen here at this conference. So physical attributes is density. The soil on the left is pretty dense. The soil on the right is not. In soil science terms, we call that bulk density. You might consider quantifying aggregates. The soil on the left has very little aggregates. It's massive. And the soil on the right, you probably could see that if it was blown up a little bit more. You would see aggregates within the soil on the right. In terms of chemical, we measure pH, we measure salt concentrations, we measure available nutrients that are present either immediately or over the longer term. In terms of biological, we measure all sorts of factors. We measure the amount of microorganisms, the type of microorganisms. We measure enzymatic activity. We measure all sorts of things as scientists. And this is the concept. The concept is, as a geeky soil scientist, we throw large nets to capture as much information as possible, and then we take that large net and whittle it down into something that's manageable or palatable in terms of describing soil health. So instead of saying, okay, we need to measure 30 different things in a soil or characteristics of a soil, we say, okay, in this situation, you only need to measure 4 characteristics. Much like a blood test. If you have a blood test drawn or done, you're not going to measure everything under the sun in your blood. It would be too costly. The same thing holds true with soil health. You want to measure only a few factors that are really important. And that's what we do behind the scenes for everything that you've heard at this conference. I'm going to show you some of that behind the scenes magic, if you will, as to what we do as scientists to try to describe some of the information you've seen over the last day or so. And at the center of all this, and you've heard this probably time and time again, it's soil organic matter, right? Soil organic matter is the carbon or the energy source for microorganisms to attack and degrade and utilize as carbon. When I teach this in my class at Colorado State University, I tell my students that we are giant walking blobs of microorganisms. We really are, right? We eat, like last night I had a wonderful filet over at this rib place. Oh man, it was so delicious. But it was carbon, it was energy for me. Microorganisms do the same thing. They use carbon in organic materials as an energy source, and they respire CO2 just like us. And I don't know if you've seen any of these pictures of legumes and the nodules, right? So if you crack open the nodules and if you look at the nodules and if they're actually if the rhizobia is active, it's pink in color, and it's because of iron. And actually, I'm going off tangent here because this is really cool. But that chemical compound is called leg hemoglobin. Hemoglobin. It's almost identical to our blood hemoglobin. Not quite, but it's really close. We're giant walking blobs of microorganisms, and we do the same thing that microorganisms do in the soil, to be honest with you. So there's a really close connection between soil health and human health. Whether you'd like it or not, there is. And at the center is carbon, because we wouldn't be alive without intaking carbon. We're carbon-based animals, basically. And so when I talk about this, I love these pictures. Why is carbon so important? Carbon is highly important for physical, chemical, and biological attributes in soils. And I want to show you a physical attribute. These are pictures from Dr. Ray Weil. He's a famous soil scientist at the University of Maryland. and he probably commissioned one of his poor undergrads or graduate students to pull aggregates out of these soil conditions. So the soil on the left, aggregates were carefully pulled out and put into this beaker from 25 years of continuous corn. The soil on the right, the soil was under 20 years of continuous sod and then broken out and put into 5 years of continuous corn. You can see the aggregates, they look nice and neat. And then this is what happens when you add water to these beakers. Poof! The soil on the left disperses. It's not dissolved, but it just breaks apart. It falls apart. While the soil on the right is held together. You can still see the aggregates. And then there's some cute little labels here, low organic matter, high organic matter. And that tells you absolutely nothing. So let me tell you something. The soil on the left has about 1% organic carbon. The soil on the right is 1.4. And if you converted that to organic matter, 1.7 versus 2.4. You know, and those numbers are not that drastically different from soil organic matter contents in the western U.S. Of course, we have areas that are lower than this, but you're only talking about not even a 1% increase in organic carbon content or organic matter content to force a huge change. And if you think about these systems, how they were treated, this soil on the left was under continuous corn for 25 years, and it was probably tilled probably every year, I'm guessing, while the soil on the right was covered and stayed put, if you will, for 20 years of its lifetime before it was put into this beaker. You know that organic carbon or organic matter acts like a glue, and if you can build this up in your soil, however you do it, that it holds soil particles in place and prevents them from moving off-site either due to water or wind erosion. Maybe not prevents, but it lessens the likelihood of that occurring. And in the western U.S., you know, I mean, oh my gosh, wind erosion is, well, both wind and water erosion are king. But wind erosion, I lived in southern Idaho for 10 years of my life, and the Dust Bowl happened every summer. I could see it. I drove into it and had to turn my headlights on at noon going down I-84 through southern Idaho, almost every year. So this is what we want, right? In the top left, we want to be able to see aggregates. We want to keep soil armor or soil cover, however you do it. And we don't want that. And maybe some of you have seen this before in the bottom right-hand corner. I've seen this in Colorado when we get these 500-year rain events, and there's no place for the water to go except for off the field instead of down. And I work with producers that follow the 5 principles of soil health practices from the NRCS. And when they get 500-year rain events, the soil doesn't do that, or the water doesn't do that. It actually goes down. It's really impressive. So this is what we do. Okay, behind the scenes, I'll call it magic. It's not magic. There's a lot of work that goes into what I'm going to show you, but we look for, or we quantify physical, chemical, and biological attributes of a soil, and we look for the sweet spot where all 3 of those circles overlap. And in the center, I like to talk about soil organic carbon or organic matter. That's at the center of those 3 circles. And I try to keep that in mind. I can tell you right now that I'm not a soil carbon expert. I have enough memory in my head to be sort of dangerous, but I like to look at those 3 circles and keep it in mind that organic carbon is the basis for that sweet spot. So let me give you a prelude into the information I'm going to share with you. And this is what happens behind the scenes, all right? So has anybody ever had a Haney test done? Okay, so you get a number back, right? You get a score back. Or Cornell soil health test done. I actually use something called the Soil Management Assessment Framework. It was developed by the NRCS and the ARS. And I was indoctrinated into this program about 10 years ago from one of the people that actually helped develop that program. And this is what happens in all of those scores or those soil health tests behind the scenes that you don't see. They run a number of tests, and they base the score on the characteristics of the soil based on more is better, less is better, or somewhere in the middle is better. So this should make sense to most of you, if not all of you. So there's a number of scoring functions that happen behind the scenes that you don't see when you get that test result back. This is more is better. it says total, TOC, total organic carbon on the x-axis, and on the y-axis on the left-hand side, that's a unitless score from 0 to 10. The program I use at CSU is 0 to 1, but some people use 0 to 100. It doesn't really matter, it's unitless. The concept is pretty simple though, right? The more organic carbon you have in a soil, the better it is. And that, for the most part, is true, okay? I mean, you can go hog wild and be way off the charts, and then your system is really out of whack. You know, I could imagine that nobody in this room would ever put down 1,000 tons of manure per acre on a parcel of land. Your system will be really out of whack. All right, I've seen that before in southern Idaho, where somebody had a 7.5% soil organic matter, and they were jumping up and down because they were so happy. The system was out of whack. Phosphorus concentrations were like in the 400 part per million. Same with nitrate, nitrogen. It was out of whack. It was a disaster. All right, but by and large, total organic carbon follows the rule: more is better. And then you would analyze for total organic carbon. You would go from the x-axis up to some curve based on a soil function, and then go over to the y-axis and have a score. Less is better is bulk density, right? You don't want a brick. You want a soil that has good tilth. Of course, it's really general, and you can fall off the edge of the far left-hand side, if you will. All right, I've seen people do that before. But by and large, less is better for how dense the soil is. That's less is better, a less is better function. And then somewhere in the middle is better is available phosphorus. You don't want to be too low where your plants are going to suffer and be deficient, and you don't want to be too high or on the left-hand side where you're creating an environmental disaster, potential environmental disasters. Somewhere in the middle is better. And so this is what happens with the Haney test, with the Cornell Soil Health Assessment Test, and the Soil Management Assessment Framework Test. There's algorithms or curves like you see on these three figures that are behind the scenes when you send a soil sample in and get a number back. This is the basis of it, okay? And so this is how this works on the grand scheme of things. You collect a number of soils, you run analysis behind the scenes in the lab for those indicators. Those indicators are given a score, and then the score is integrated, and you're given a result for your Haney test, or the CASH test, or the SMAF test. This is how this works. And at CSU, we use 0 to 1. It doesn't really matter, right? But 0 being worst, 1 being best. The Haney test uses, I forget if it's 0 to 100. I think that's right. Or 0 to 50 or something. And then usually if you get a Haney test done, like at Ward Labs, they'll send you a picture back, right? And it'll be red, yellow, or green. I think that's how that works. I've seen that before, yeah. So keep that in mind, 0 to 1. 0 being worst, 1 being best. So I'm going to share with you some stories from some of the work that we've done. And this is the gap between what you've heard from other people that are doing this in the real world and people like myself that do this type of work behind the scenes to explain what your farmer or rancher colleagues probably see and do and talk about. This is behind the scenes. So I'm going to talk about a shift in land use, and this is some work that I was fortunate enough to be a part of in south central Idaho. And this is called the Upper Snake Rock Watershed. It's near Twin Falls, 220,000 acres fully irrigated. It's in the Magic Valley. It's called the Magic Valley if you don't know this. It's called the Magic Valley for a reason, because when irrigation came to this location in the US in the early 1900s, it was magic that anything could grow in this area except for sagebrush. And it's really magic. And so here's the story. This is a great story. In this area, it's 100% irrigated. I don't know anybody in this area that raises a crop that's not irrigated. And when you look at a picture like this on Google Earth from 1984, and you see a lot of rectangles, what does that tell? Is anybody in irrigated ag in here? Yeah, so what does that tell you about irrigation? What kind of irrigation is happening here? Yeah, it's flood or furrow irrigation. When you see squares or rectangles and you're under irrigated conditions, most often it's flood unless you have a wheel line, right? But 1984, there was probably very few wheel lines in here. And in fact, there's only a few pivots right? You can see a couple pivots, but in Google Earth, there's a timeline feature, which is really fun to play with, and it's up on the top, and you can slide the bar over, and if you slid the bar over, and you fast forwarded almost 30 years, look at the switch. There's a huge conversion, and I really do mean huge. It went from almost 0% to 50% sprinkler irrigation in 30 years, primarily due to the EQIP program. And so this is a really fun story, and I love talking about this project. So when you look at furrow irrigated fields, if you're a furrow irrigator in this room, you probably could tell me by looking at some of these fields which way the water was flowing, because you just know, right? I mean, you just know. So I'm going to make it simple. And if you zoom in on a field, you probably, and I'm not going to ask you this question, I'll answer it for you, just because there's only two answers, and one's right and one's wrong. The question is, which way is the water flowing on this field when it's irrigated? And the correct answer is it's flowing from right to left. This is 100 years of furrow irrigation on this property, at least 100 years. And the topsoil has been eroded from the right-hand side, exposing the subsoil, which is highly calcareous, white, light-colored. And that topsoil has been either moved to the bottom of the field, or it's gone. It's probably in the Pacific Ocean by now. It's moved into the Snake River and down the Columbia out to the Pacific. It's gone. And it's a real shame. So this is what we did. In this area, we found 4 producers who all owned either furrow irrigated land, or they had converted a parcel of their land over to sprinkler irrigation within 5 to 8 years before us setting foot on that property. And we came along and we soil sampled the tops of all those fields, and we soil sampled the bottoms of all those fields under furrow or sprinkler irrigation, and we analyzed them for soil health characteristics. So this is the question we had. If you were to take a furrow irrigated field and convert it to sprinkler irrigation, how long does it take, or does it actually affect soil health? Does this bottom right-hand corner affect soil health? And so what did we find? I'm going to keep this simple. So the furrow irrigated fields, this is the part I really like, because you don't have to have a PhD. You don't need to be a rocket scientist to know this. If I was going to ask you what portion of the field has better soil health, the top or the bottom of the field, what would you say? The bottom, right? You said that in the picture I showed you between the tilthy soil and the brick. And you would be right. You don't need to spend your whole life in academia to tell me this. Like, I could have done this when I was in high school. I could have easily done this. If somebody just gave me a little bit of information, I could have said that, and you'd be right. So the chemical, biological, and nutrient indices that we quantified, and I'm not going to tell you all the background into those. I'll share with you the minimum data set here in a second. But the field bottoms were always greater than the field tops. Duh. Right? This is like a no duh, Jim moment. It's going to be greater because there's more organic matter down there, and there's probably more biological activity at the bottom of the fields, et cetera, et cetera. And you would be right. Yeah, that's a great question. The question was, is that a bad slope on that field? That slope is about 1%. So this entire area in the Magic Valley was graded early on in the early 1900s to be about a 1% slope across the fields to force water down due to flood irrigation. So it's not very steep. And I can tell you that the issue in this area, much like the western U.S., is our topsoils in the western U.S. are fragile, right? We don't have a whole lot of topsoil to begin with out west, maybe a foot. And so 100 plus years of flood irrigation has pushed that topsoil off this site, which is really a shame. And that subsoil, it could be up to 40% lime. It's dominated by calcium. And then there's a hard pan in there. You can talk about negative soil health attributes, right? It's really tough. But this is a great story, so bear with me here, right? So when we combine the indices together for overall soil health, always the field bottoms had better soil health than the field tops overall. And this is where we take, as soil scientists, This is the behind-the-scenes magic that you don't see in some of the other talks that you've seen today and yesterday. We cast a wide net. We whittle that net down to what's important. And what's important in this site is clay content. There's a little bit greater clay content in the bottoms of the fields versus the tops. Certainly more soil organic carbon. Increase in available potassium, which may or may not be, it doesn't matter that much if there's just more potassium in the bottom. Our soils in the western U.S. have plenty of potassium. The bulk density actually goes down, and there's an increase in something called beta-glucosidase activity. This is the ability of microorganisms to break down cellulosic material, and it probably has something to do with what Jill was talking about right before you came in here, about the amount of fungi that's present. Now, we didn't quantify that, but beta-glucosidase is an indicator of decomposers. So it probably has something to do with the amount of fungi that's present in the bottom of this field. The interesting part about all this was that 30 years ago, there was a scientist at this location in south central Idaho that noticed that the field bottoms across this magic valley always out-yielded the field tops. And so we made a connection from something that happened 30 years ago to now based on soil health. And okay, that's fun. This is where it gets really fun, all right? So the system had been under flood irrigation since the early 1900s. This project started in, I think, 2016 or 2017. No, it was 2015. And we went out to these sprinkler irrigated sites, had been converted from furrow to sprinkler irrigation 5 to 8 years prior to us setting foot on these locations. And what did we find? We found that the soil health was equal in the field tops and the field bottoms. And I'm not going to share with you any minimum data set because every indicator was not statistically different from every other indicator in the field tops and field bottoms. And so this is where I'm going to tell you as a scientist a really fluffy answer. And the fluffy answer is I think that soils have a memory, and if you start treating them well, that they respond accordingly. And this is a story of treating your soil well, simply by converting from furrow to sprinkler irrigation. And it happens quickly. I mean, 5 to 8 years after treating your soil poorly for 100. It's pretty impressive. I know it's a fluffy answer, but that's how I like to look at it. I think soils have a memory. So I'm going to switch gears. And this is also a story of production ag. And this probably doesn't correlate to most, maybe not anyone in this room. So I run a long-term biosolids land application program at Colorado State University. And it's much like adding manure to a soil, to be honest with you. This program has been going since 1982. I've been involved since 1991. And we apply biosolids at agronomic rates to croplands, actually dryland cropping systems, under wheat corn fallow or wheat fallow. And we also apply this material to grazing lands north of Fort Collins in Colorado. And so here we are applying basically human manure, probably right before wheat planting, I'm guessing, and then human manure out on a pasture land that's used for cattle. And we compare all of this to, in this production ag setting, we compare it to inorganic fertilizers under no-till. And in that system, of course, it's under no-till. These are all surface applied, no incorporation. We compare this to inorganic fertilizers, and over here we just compare it to a control, so nothing added. And we have increasing rates in this system, and we have an agronomic rate in this system. I'm going to keep the story short. So we've been doing this for quite a long time. And this is what we find, and you can look at this list. We either see positive trends or we see significant differences compared to either control or an inorganic fertilizer that a producer would use in terms of using this organic amendment. And a lot of it's probably driven by the input of organic carbon, which simulates physical, chemical, and biological attributes in the system. And it's too bad this is all cut off. You know, at the end of this presentation, I'll show you my email address. If you ever want to have some good bedtime reading, a lot of this has been published recently, and I'll be happy to share it with you. You just can't see you can't see it at the bottom here. But we see either positive trends in all of these attributes, or we see significant increases or improvements when we add this organic amendment to a system. We're actually doing this right now with manure on some degraded farmland at our research farm. And I don't have data to share with you today, but maybe in a couple years. So I want to switch back to irrigation. This is another project that we started 2016 or 17 over in Furrow, Colorado, near Grand Junction. And I like this project. And it'll probably be really apparent here in a few minutes why I like this project. So this is a project that deals with conventional versus minimum till and furrow irrigation. And if you are a furrow irrigator, you probably would scratch your head, like, how are you going to pull this off, Jim? All right? And there's some challenges in furrow irrigation with minimum till. Actually, there's still some tillage, right? Because you have to create the furrows. But there's some challenges, and the challenges are this. So we had conventional versus minimum till in this section of the field that looks like relatively big blocks. There's 4 replicates out here. We had conventional till or minimum till interspersed within this field in the big blocks. And then what we did was we altered the residue management. This was all under continuous corn for 3 years. We either grazed the residue, so we put fence out around the plots that needed to be grazed with either cattle or sheep. Can't remember which years we used one or the other. We kept the residue in place, or we simply baled the residue and removed it. So conventional till, minimum till, and then those residue management scenarios. And the way we managed the residue in place was with this implement called a crimper. And the crimper is actually a really simple but effective tool for furrow irrigation. So if you're a furrow irrigator, you know that if you have residue in place and that residue is in the furrow and you've put water down that furrow, where does the water go? It goes everywhere you don't want it to go. It goes horizontal instead of lateral down the furrow, because these residues create dams and dikes in that furrow. So the water goes wherever you don't want it to go. So what this crimper does, it's a really cool device. You can see it in this top left-hand picture. It takes the trash or the residue in every opposite furrow and tosses it into every other opposite furrow. So you irrigate down the ones that look relatively clean, and you don't in the one that looks full of trash or residue. And here's a good picture of it right around the 4th of July with the residue in place in the furrow that you don't irrigate. It actually is really effective, and it keeps the soil covered, and it adds organic carbon back to the soil over time. And so what did we find? So here's a big table full of numbers. The scores are from 0 to 1, and they're sort of irrelevant. But 0 to 1, 0 being worse, 1 being the best. And then if you look at this, do you see the mouse? Yep. No. Can't see the mouse. Okay. So I'm going to try to keep this simple. So we pulled soil samples from 0 to 15 or 15 to 30 centimeters. And then on the very top left is how we manage the residue. We baled it, we grazed it, or we retained it. Then if you move over a little bit, we compare conventional tillage versus no-till. And then on the far right-hand side, or far left-hand side, are the physical, chemical, nutrient, biological attributes and overall soil health. All right. And let me walk you through this. So let's start in the 0 to 15 and 15 to 30 centimeter depths for how we manage the residue. What we find is, for most of these attributes or soil health indices, we don't see any differences. Okay? But this is where it gets fun. In the top 15 centimeters, this is how this works in these programs, like the Haney test. So you might not see differences in some of the physical, chemical, or biological attributes, but when you combine those all together and integrate over all of them, as in this case, you see a significant improvement. And what we see is is that if you graze the residue or you keep it in place, that the overall soil health, when you add up physical, chemical, and biological attributes, there's a significant improvement in soil health in that system in the 0 to 15 centimeter depth. And if you want to see an improvement in soil health, and you've learned this over the last day or two or elsewhere, that where do you want to see the best bang for your buck? When you talk about soil health, you want to see it near the soil surface, right? You want to keep that soil in place so it doesn't erode off site. Improving soil health in the soil surface is highly important in this system, and this is data that was collected only after 3 years of implementing this practice. Short time period where you start seeing changes. And in fact, the changes are due to improvements in water-stable aggregates, lower salt concentrations, improvements in extractable potassium. There's beta-glucosidase activity, probably it's fungal associated. Something called PMN, potentially mineralizable nitrogen. That's how much nitrogen is present in the organic form that can be released and available to plants over time. Slow-release nitrogen fertilizer. It's really what it is. And an increase in microbial biomass carbon, or microbial activity, all in the soil surface. Now, if you look at how you manage that conventional versus no-till with that crimper in the soil surface, if you look at those values in those two columns, more often than not, you see an improvement in no-till. Not always, but almost always. And if you look at the overall soil health in the 0 to 15, no-till improves soil health over conventional till. And that's where you want to see the improvement, right? Near the soil surface. And in fact, that's due to a reduction in electrical conductivity. There's beta-glucosidase again, microbial biomass carbon, and greater soil organic carbon in this system. Under no-till versus conventional. All the things that you've probably learned, right, over the last day or so. And here it is from a scientific perspective. And then if you look at the below ground depth, these numbers in these two columns actually flip, and soil health is favored under conventional till, and we think that's simply due to some stratification that's occurring within the no-till. And so you see improvements in the 0 to 15 under no-till because the material has been moved up over time, and it's improving the above ground or the very close to the surface part of the soil, and the subsoil is actually lacking behind. I don't know if this is ever going to catch up because this is how it works at the university system, that you're funded for 3 years and then the project is poof, gone, okay? It really does happen that way. And so that's just the nature of funding, unfortunately. It would be really cool to see if this bottom depth flipped over time, but we ran out of funding. Okay, how am I doing here? Okay, I'm getting there.
What about tonnage? Did you check that?
Tonnage in terms of yield? Yeah, I'm glad you asked that question. The question is, what about tonnage in terms of yield between conventional and no-till? And I should know that answer because that data was just published 2 days ago, and I can't remember what the outcome was. So I'll pull it up on my no, I don't have my computer here with me. Track me down later. I'll be around. I'll get my computer if you find me and ask me that, and I'll show you. I just can't remember what the yield differences were. Yeah, that's a great question.
Did you see it?
I can't remember, to be honest with you. So this is how this project worked. So I don't work in Furrow, Colorado. I work in Fort Collins, Colorado, 5 hours away. And so my partner in crime, who was a research scientist over in Furrow, he did the bulk of that work in the in-field work, and I did the soil health work. So he took part of this project and published yield results, and I published the soil health results. And I should know it off the top of my head, but man, I'm drawing a blank. I don't even know my name half the time. But that's a great question. And I'll see if I can find the answer. I can't remember. So I want to switch gears and tell you another story, because this is a soil health story that deals with integrating livestock into systems, which is one of the 5 practices that is promoted from the NRCS, right? So this is obviously it's a pivot, at our research farm north of Fort Collins, where this field was under production, conventional production ag for at least 10 years before we got our hands on it. I can't remember if it was continuous corn, or I don't think it was continuous corn. There might have been alfalfa in there, but it was under conventional ag. And I know it was in corn before we converted it to a perennial pasture system. It's fully irrigated. And within this system, you see polygons. Can you see those? So those polygons represent electric fence. And this is something that, as a producer, you probably would never do. But this is a project on management-intensive grazing. So taking the cattle herd that we have on our research farm, which typically lives down here in the bottom left-hand corner, and putting it out in this pasture and moving this herd every 3 or 4 days based on how much they consume within each one of those paddocks or polygons. So we had a graduate student who loved soils and actually loved working with animals, and she got to drop the electric fence and then put it back up and move the cattle. And she loved it. And so here's some pictures. Top left-hand corner, the animals were just moving into a new paddock. They grazed in the top right-hand, and when roughly 50% of the above-ground biomass was removed, the electric fence that you see in that picture, that white line, was dropped and they moved over into the other paddock. And this ties in with some of the concepts that Joe was talking about before we came in here, right? But the concept is to not, in this case, was to not stress the plants too great. And the person I work with, who's a rangeland specialist, says about 50% of above-ground biomass should be removed so you don't stress the plants, so those stored carbohydrates in the roots aren't forced to be used up to reproduce or grow more plant above ground. And that was the rule of thumb that we used. So we took these animals and we moved them all over this pivot. That's what it looked like. And then we soil sampled 1 or 2 years after we established this project in where all those circles are. And then there's no circles in the top left-hand corner because that blew out. That's the northwest corner, and guess what? Winds in Fort Collins, much like in Utah, come from the west or northwest, and it killed all those plants at one point in time. So we never soil sampled out of that. So we soil sampled on those dots, and what did we find? And this is what we found. And I don't know if I need to go through all this. I'm going to keep this simple. Let me just throw some things up here. So what you see, and I don't show you the whole story, but I show you physical, chemical, nutrient, and biological, and then overall soil health improvements. And what we typically find is that physical soil health actually goes down a little bit due to trampling. Not surprising, right? So an increase in bulk density. We see some chemical attributes increasing, and that's due to salts being leached out of the system over time. We see nutrient soil health actually decreasing, and that was due to phosphorus becoming less and less available to the plants. And I actually think that this is a good thing in perennial systems, to not have excess phosphorus in the environment and keep a system that's relatively closed-looped. And I mean, we've never seen a phosphorus deficiency in these plants, but make the system less leaky, if you will. In terms of biological, we see improvements in biological soil health over time in beta-glucosidase, microbial biomass carbon, and potentially mineralizable nitrogen. And we think that these are early indicators. In fact, the literature tells us these are early indicators of improvements in soil organic carbon. So this work happened in 2017 and 18. We're following up right now in 2021 and 2022 to see what happens in the longer term. And I don't know I don't have any data to share with you. We just started this last summer. But I hope it shows positive trends over the longer term. Okay. So that's the geeky scientist part, or the science part of this talk. Now I'm going to switch gears and I'm going to tell you some things that we're working on that are much like what's going on in Utah and other places out west. And one of these projects, we started this last year, and this was, it's a CIG project, much like what you have here in Utah. Okay, it's funded through our Colorado Department of Public Health and Environment, not the CDA or Colorado Department of Ag, but it's a 319 project. And we landed this project, and we have 5 producers we're working with. We're focused on soil health in conjunction with changing best management practices in agroecosystems. So some of the systems that we work in have conventional till versus strip till versus no-till or minimum till. We have another system where we've converted a producer, I shouldn't say we, a producer's converted from flood to sprinkler irrigation, which ties back into that story I told you earlier. And we have edge of field water quality devices. So what we're trying to do, with a 319 program, it's based around water quality, right? And so what we're trying to do is state that if you change a management practice in a field, how does it affect water quality? And then in between, how does that affect soil health? And can we tie these three together? So we're working with 5 producers along the Front Range to do this. No, I have no data yet. I love my job, and sometimes I love it so much I have to work in the mountains, which is a real shame, all right? So that big picture, that picture with my big smile on my face at the very first slide, that's this site here, okay? So I work in mine land reclamation and looking at soil health and how reclamation affects soil health and plant productivity and hopefully does not degrade animal health. So this picture on the left-hand side is from near Leadville, Colorado. It's a Superfund site. Heavily contaminated due to historic mining in this area, specifically silver mining in the late 1800s, early 1900s. The picture, the inset, is essentially the same picture as what you see in the background. The inset, that white, is not snow. It's salt. It's a metal salt. It's zinc sulfate, 30,000 to 60,000 parts per million zinc as zinc sulfate. There's a reason why plants aren't growing here, because they can't grow in that material. What's happened over time in this area, much like historic mining operations in the western U.S., you mine for the ore, you remove what you want, and you toss the rest over your shoulder. And the rest over your shoulder went into the upper reaches of the Arkansas River. They washed downstream, and they hit a bend in the stream and were deposited as we call them alluvial mine tailings. This site, that was a picture taken, the inset, in about 1985. Some people came through in 1995, added 100 tons of lime to raise the pH. pH was about 3 when it started. Now it's 7. And they added 100 tons of biosolids, an organic material. Then it was reseeded with a seed mix from, I think, the U.S. Forest Service. This picture, I took this picture, almost the same spot as that other picture. This picture is from 2019. Looks pretty good, right? I've worked on this site a few times in my career. We came through, and I kind of knew where to look for soil health based on some previous work. I can tell you that the soil health in this system is, for the most part, pretty good. If I was to show you data, you would say, oh, that looks pretty good, but I'm not going to show you data because I'm going to run out of time here. But the data will tell you that, and this is something you don't get from a Haney test or another test, they don't tell you anything about trace or heavy metals in systems. They don't. So one of the programs we're running at CSU is to try to build in those tests into our soil health program. And I can tell you for a fact that this site, in terms of soil health, is relatively degraded in terms of the metals that are still present. The concept behind adding lime is to raise the pH, to drop the metals out of solution. They become insoluble. They form minerals, but they're not quite insoluble. And you can see that signature in the soils, and you can actually see the signature in the plants, in the above ground tissue. And if I was a producer only feeding this forage to my animals, I wouldn't. Yeah, it would be a big problem. There's excessive cadmium and excessive lead in the above ground tissue. They look great, but they're not great. Luckily, this area is only a few acres. And yeah, browsers come through here. There's some horses that are grazed out here, but they don't primarily graze this area, thank goodness. This is the story I'm trying to tell you in terms of heavy metal contamination in the environment. And the same thing holds true for these two pictures. One, bottom right-hand corner is down near Telluride in the Box Canyon there, and the other picture is over just east of Ouray. And same concept. We're looking at these mine-capped areas and heavy metal contamination and above-ground plant contamination, potentially. It's really fun because hardly anybody does this sort of work in terms of soil health. Let's see. I'm going to tell you a quick story here about what we're doing in Colorado because it's almost identical to what is occurring in Utah. So you have, what is it called, the Soil Health Partnership in Utah? In Colorado, we had the Colorado Collaborative for Healthy Soils. I spent the last 2.5 years of my life being consumed by this. And we focused on a number of different factors that affect soil health and promoting soil health in Colorado, much like you're doing here in Utah. And we're actually, step by step, we're following Utah very closely. In July of 2021, our House bill passed. It's a voluntary soil health program in the state of Colorado. There's funding in place to be used for soil health programs, and we've established a soil health program in Colorado, much like here in Utah. And what we've done is create, among other things, something called the STAR program. And I'm really proud of this because this program that we've developed in Colorado has been really grassroots effort. We work side by side, producers, ranchers, etc., scientists like myself, people at the state level. We've all come together to put together this program called the STAR program, Saving Tomorrow's Agricultural Resources Program. And the way this works is, and if you want to go to this website, that'd be great. Within the website, we have a number of forms. We call them STAR forms. Depending on the type of producer you are, or the type of crop you're growing, or animals you're raising, if you're a rancher, you pull out a STAR form, you fill out the form. It's based on the 5 principles of soil health that is promoted by the NRCS. It's embedded in the form. You might not be able to see it, but it's embedded. That form, depending on your answers, gets scored. And you get a 1 to 5 star rating. And I'm going to skip some points here. But this is what happens. You get a 1 to 5 star rating, 1 being you're about average to what everybody else is doing. So if you're growing dryland corn, and that's your primary crop, or dryland wheat, if you get a 1 star rating when you fill out the form, you're about 80%. So that means you're doing anything wrong, but you're about average. Versus 5 star, you're practicing the 5 principles of soil health promoted by the NRCS. So we've actually worked with the NRCS on this as well. The producer receives a placard, goes out in their field with a concept that I can't do because I'm not a sociologist, but this is a project in sociology to see if change can occur simply by placing these placards in producer fields to generate interest and discussion as to, hey, Bob, why did I get a 1 and you got a 2? And to generate discussion to think about change. And that's the premise behind this program in Colorado. We are implementing this on 150 fields this year across the entire state with support from 2 CIG projects, 1 state and 1 federal, and a conservation partnerships project through National Fish and Wildlife Service. And it's only, I heard Jay talking about 20 million and 50 million, and we're doing this on $5.7 million with a boatload of people. But we're going to try to do it and see how this turns out. So the concept is this. I've got like 2 minutes. The concept is this. So we're going to have all these fields within this program. We're going to be quantifying soil health in our laboratory. We're going to be quantifying stars based on the forms that people fill out. And we're going to try to correlate the star ratings with soil health measurements over time, over the next 4 years, to see if we can keep this make this program simpler, right? So instead of you having to go out and take a soil health measurement every year, every other year, every 5 years, all you need to do is fill out the star form, and that might tell you a heck of a lot of information about your field without actually having to pull a soil sample. So this is sort of the direction we're going in Colorado. I have some other slides, but I'm going to stop there and see if there's any questions. Thanks for your attention. Questions? Yeah. Yeah, that's a great question. The question is this going to be comparing neighbor to neighbor or somebody in eastern Colorado versus the west slope of Colorado? And, from my perspective, I'd rather compare neighbor to neighbor because the situations or scenarios are similar versus, like in northeastern Colorado, they might get 16 inches of rainfall per year versus the southwestern part of the state that gets 6. The comparison just shouldn't be made. And so, that's actually my school of thought too, in terms of soil health, that we shouldn't be comparing soils in Utah to my home state of New Jersey. Like, there's no comparison, right? So we're going to try to keep those as separate as possible. I don't know if that's going to be the entire case, but that's the direction we're going. That's a great question.
So with the star, so there's kind of one system, like
Yeah, exactly. So the question is, how do we score the STAR program? So, I'm not kidding. This has taken like 2 years of my life to work with people to come up with 9 or 10 sheets to score soil health, because everybody has a different opinion on how we score this. But we've taken a lot of input and put it into this program to come up with scores. And so it's weighted. I can tell you that the scores range from 0, which nobody will ever get, to some number like 87. And it's a weird number, right? You don't see this behind the scenes, but this is behind the scenes. And then we have a 1-star rating is a rank between like 0 and 12 on the sheet. 2-star is 12 to 24. 3 is, and so forth and so on. But this input was, or that form, that scoring form is based on input from, I'm not kidding, from a lot of people. Mostly producers. We let the producers drive the input, and then we massage the form into submission based on some science behind it as well. So we work hand in hand, yeah. And the forms, I'll go back. Did it go back? The forms should be found on this website. And I don't think all the forms are up there yet. There's one form in particular that we're still working on. So if you're interested in this program and you're a rancher, we're still struggling with how we're going to put that form together. But it'll be up there soon. But we have, I think, 9 different forms up there already. Yeah, you can go check it out. Yeah.
basically you said the farmer and rancher fills out the form and you give him a point score. And then 100 of them are going to receive flags. Put in their form for people. And then it said something there, then are you going to go out and do soil tests annually to see if they improve, or they just get the one soil test to see if they're working?
Yeah. That,
Because you're giving the star based on their answers, not a real soil test. Is that correct?
That's correct. So the STAR form and the placard that they receive to go into their field is based on the sheet that they fill out that's found on this website. In conjunction with that, I'm not kidding, there's like 150 farms that our team at CSU has to visit this summer and pull soil samples from and quantify soil health behind the scenes. And we're doing this, and I'll keep this simple. Let's make believe it's a 4-year program. It's not. There's some that are 3 and there's some that are 4. But we'll pull soil samples in year 1, and then we'll pull soil samples in the last year to see if there's change. And so we run that behind the scenes. And in year 1 and then year 4, the producer will fill out the STAR form in both of those years to see if something has changed. And we're going to correlate, hopefully, that change or lack thereof with what we see in the soil health testing program.
So the idea is to give them a star of 2 to 5 stars, and then see if they'll try to improve their stars by following some of the 5 practices.
Exactly. So we have to work with producers that are curious. I mean, every producer I've ever worked with in my career has been curious about something. But, they need to be curious enough to make a commitment to a 3 or 4 year program in terms of changing a practice. It only has to be one change, but we need to compare sort of business as usual to something that's they want to do and look at. And it doesn't have to be a large scale. Like, we're looking at only a few acres, but a few acres could make or break somebody. So we're looking for producers, actually we're in the process of doing this now, is looking for producers that want to be a part of this, that want to I shouldn't say sacrifice, but yeah, kind of sacrifice a portion of their land to try something new. to see if it forces change in soil health and water quality, or actually water quantity is another portion of this that I didn't mention. So water quantity, increasing the size of the bucket in your soil is what we're looking at too in some locations. Lunch? All right, thank you. Yeah, thank you.